What if I told you that the slice you've been, desperately trying to fix for the last 10 years has absolutely nothing to do with your golf swing?
Yeah, that is a tough pill to swallow for a lot of players.
Right. What if that well-meaning instructor or club fitter actually handed you the exact wrong piece of equipment to fix it? Today, for you listening, we are completely demystifying the diagnostic muddy waters of the golf swing.
We really are. We're diving into the actual physics of the golf shaft.
Exactly. We're uncovering why traditional club fitting might actually be working against you.
It really is a paradigm shift. We're basing this deep dive on some incredible insights from Michael Neff. He's the CEO of Gears Golf, and he recently broke all of this down on the Athletic Motion Golf channel.
Yeah, and for those unfamiliar, Gears isn't just a standard launch monitor that tracks the ball.
Oh, not at all. It uses advanced optical motion capture. I mean, picture a Hollywood special effects studio. High frame rate, high megapixel cameras placed all around a room, tracking, millions of sub-millimeter data points on both the golfer's body and the club simultaneously.
It's essentially a high-resolution MRI for your golf swing. And by the end of this deep dive, you are going to understand why a perfectly good swing produces terrible shots with certain clubs.
And why the advice you've been hearing about shaft torque for decades is, well, it's completely backwards.
Okay, let's unpack this.
Yeah.
To understand how to fit a shaft, we first have to understand what the shaft is actually doing during a swing. And spoiler alert, it is vastly more chaotic than it looks on television.
So much more chaotic. When we watch a tournament on TV, the shaft looks like a rigid metal or graphite stick. But let's look at the timing and the physical forces involved here.
Right, it happens so fast.
Extremely fast. A typical Tour Pro's backswing takes roughly 3/4 of a second. The downswing is less than 1/4 of a second. And in that tiny window, the club head is accelerating to speeds over 155 miles per hour.
And in that fraction of a second, that shaft is engaged in a violent physical tug of war. I mean, it is simultaneously bending backward, drooping downward, deflecting forward, and twisting around its own axis.
All at the same time.
It's crazy. Imagine trying to control a wet noodle, or like cracking a highly specialized whip at 150 miles per hour and expecting the very tip of that whip to hit a target the size of a dime perfectly square.
Which is exactly why we haven't historically understood this chaos. Our perception has been entirely warped by the cameras we've used for decades.
This is the rolling shutter effect.
Exactly. Traditional cameras, especially older smartphone cameras, use a rolling shutter. They capture an image by scanning line by line from top to bottom.
Oh, I know exactly what you're talking about. You see those still photos online where the golf shaft looks like it's bending backward into this massive U shape right before impact.
Yes.
And the comments are always full of people saying, oh, look at that incredible lag.
I actually used to teach based on some of those photos, but it's an optical illusion. Because the club head is moving so fast, by the time the camera's sensor scans the bottom half of the frame, the club head has already moved past where the shaft was in the top half of the frame.
So it artificially bends the shaft in the image.
Right. That's why optical motion capture technology is so revolutionary here. It strips away the shutter illusions and gives us the actual three-dimensional XYZ movement of the shaft in space.
And the data it reveals about human variability is just staggering. Neff points out that no human being, not even Tiger Woods in his prime, has ever made the exact same golf swing twice.
You physically cannot replicate the exact same forces and torques.
Right. They even put clubs on mechanical testing robots, and those robots show micro variations just because of how the robotic hand grips the handle and the way the shaft vibrates at the top of the swing.
This touches on the fundamental nature of the game. We are constantly trying to control an inherently variable system.
But wait, let me push back on that for a second. If the human swing is this chaotic and literally impossible to replicate perfectly, even for a machine, how can we possibly measure it accurately enough to fit a club? If the input is always different, isn't the output just a massive guessing game?
That is the exact paradox that makes this so fascinating. The variability of the human body is precisely why we need optical motion capture, and precisely why the golf shaft needs to be the anchor.
Okay, I'm tracking.
Because we cannot perfectly control our bodies, we desperately need the shaft's behavior to be completely predictable. If your brain is making split-second micro-adjustments on the downswing, but the shaft is reacting in wildly unpredictable ways, you have zero chance of consistency.
You're just fighting the club.
Exactly. We have to isolate the variables, starting with the instrument itself.
So if we absolutely need the shaft to be this perfectly predictable anchor, that begs a massive question. Are the shafts we buy actually predictable?
Well, that brings us to how they are manufactured in the first place.
Right, because the data reveals a shocking reality about how these highly technical instruments are built. We're talking about a manufacturing process called sheet wrap versus a newer method called filament winding.
Yeah, for decades, the industry standard for traditional graphite shafts has been sheet wrap. It's a highly manual process.
And it is exactly what it sounds like. They take a metal rod, which is called a mandrel, and a human worker literally rolls sheets, think of them as big, sticky graphite flags, around the rod by hand.
It's shockingly similar to someone hand rolling a cigar.
Which seems insane for a precision instrument.
It does, and because it's a flat sheet being rolled onto a cylinder, it inevitably creates a seam where the material overlaps. That seam acts like a rigid spine down the length of the shaft, creating structural inconsistencies.
So it bends differently depending on how you hold it.
Yes, it will physically bend differently depending on which way that seam is facing during the swing.
The gears data highlights a robot test conducted in Korea that absolutely blew my mind. They put the #1 golf shaft in the world, a premium, very expensive sheet-wrapped shaft, on a robot.
Right.
They hit 5 identical robotic swings. The deviation in how much that shaft drooped or bent downward was about 10 millimeters. Now, 10 millimeters sounds tiny in a laboratory.
But downrange.
Downrange, at the target, that translated to a 10-foot radius of error on perfectly identical swings.
10 feet of dispersion strictly from the manufacturing inconsistency of the shaft. I mean, the robot did nothing wrong. The instrument failed.
But then they tested a shaft made using a newer machine-driven process called filament winding.
And this process sounds like science fiction compared to the cigar rolling method.
It really does. Instead of sheets, they run single strands of graphite through a resin bath to remove any microscopic air bubbles. Then, a computer-controlled machine weaves and wraps those single strands seamlessly around the mandrel.
Right. No stickers, no overlap, no seam.
And the results.
The results from the robot test completely validate the method. The filament wound shaft had a droop deviation of less than 2 millimeters, which translates to an incredibly tight 2-foot radius downrange.
Wow. From 10 feet down to 2 feet.
Exactly. It is virtually uniform 360 degrees around the shaft. And because there is no seam, you completely eliminate the need for puring.
Okay, let's clarify puring for a second, because a lot of golfers pay really good money for that. Puring is that expensive process fitters use to find the spine or seam of a sheet-wrapped shaft so they can align it facing perfectly down target, right? Just to make the club playable.
Yeah, and filament winding makes that entire process obsolete.
So my immediate question is, if filament winding is this vastly superior and it practically eliminates downrange dispersion, why isn't every major golf company shouting about it from the rooftops?
It comes down to industrial economics and supply chains. Changing a global manufacturing process is incredibly expensive.
Oh, I bet.
Filament winding requires entirely different robotics, different software, and different engineering expertise. For massive companies that produce millions of clubs a year, adopting this disrupts their current highly profitable manufacturing model.
I see. They already have the factories built to roll the cigars.
Yeah, they aren't going to burn down their own profitable factories just to give us a 2-foot dispersion.
That makes total sense, sadly.
But from a modern, high-tech fitting perspective, this precise manufacturing is the future of the game. Let's think about the physics of shaft movement, specifically the relationship between shaft flex, loading, unloading, and timing.
Right.
The entire job of the shaft is to store energy during the transition at the top of the swing and release that energy squarely through impact. When you have a perfectly symmetrical filament wound shaft, the golfer experiences a distinctly different feeling.
Because it's finally loading and unloading with perfect consistency.
Exactly. The golfer feels a true connection to the club face. When the shaft behaves predictably, it removes the subconscious doubt that your equipment is failing you.
And your brain stops sending panic signals to your hands to manipulate the club face at the last millisecond.
You nailed it!
I love that. When you trust the physics of the equipment, your body can just swing freely. Now, because filament winding gives us these incredibly precise, seamless shafts, it has allowed data analysts at Gears to isolate variables and expose a massive flaw in traditional golf teaching.
Oh yeah, this is huge.
Here's where it gets really interesting. This is all about shaft torque. Wait, let's make sure we really absorb this next part, because what we are about to discuss contradicts basically every golf magazine printed in the 1990s.
It really does. Torque, in the context of a golf shaft, refers to how much the shaft twists around its own vertical axis.
Right. And the old PGA school myth, the one taught to millions of amateurs, is that a shaft with low torque, meaning it's very stiff and resists twisting, will make the ball go right.
Yep, that's what we were told.
And a shaft with high torque, a softer twisting shaft, will help you turn the club over and draw the ball to the left.
But the optical motion capture data proves the exact opposite is true. The physical reality of a golf swing flips that conventional wisdom completely upside down.
Let's walk through the actual mechanics of why this happens.
Mhm.
You have to visualize the centrifugal forces at play during a downswing. You are swinging a metal club head around your body.
Exactly.
The softer the shaft, meaning the higher the torque, the more that shaft droops. Droop is when the club head physically pulls outward and drops toward the ground during the downswing.
Let's visualize the 3D geometry of what happens when a shaft droops. Imagine holding your 7-iron out in front of you. If the club sits flat, the loft points straight forward. Now, physically push the toe of the club down toward the ground, mimicking that droop.
Okay.
Where does the face point now?
Well, the loft physically tilts sideways. It points to the right.
That is the hidden mechanic. When the shaft droops downwards, it forces the club face open, and it dynamically increases the loft.
Open face, added loft, meaning the ball goes high and it goes right.
Every time.
And conversely, a stiffer, lower torque shaft resists that centrifugal droop. It stays more stable, keeps the toe up, keeps the face squarer, and naturally sends the ball lower and more to the left.
It is entirely a physics problem based on the center of gravity shifting. Michael Neth uses this brilliant analogy about Iron Man that helps visualize the twisting forces.
Oh, right, the vibranium shaft.
Imagine Iron Man is holding the club head tight in his hand. And the shaft is made of pure vibranium, so it's infinitely stiff, absolutely zero torque. If you twist the grip in your hands exactly 1 degree, the club head twists exactly 1 degree. It's a perfect 1-to-1 ratio.
But let's take that a step further to really explain the mechanism. Why does droop destroy that 1-to-1 ratio?
Think of it like carrying a heavy bucket of water.
Okay, so with your arm perfectly straight down by your side, you can twist your wrist pretty easily.
Right, but now raise that heavy bucket straight out in front of you, parallel to the ground. The center of gravity has shifted way out. Suddenly, it is incredibly difficult to keep your wrist from twisting under the weight.
That is exactly what happens with shaft droop. As the club head droops further and further away from the original axis of the shaft, its center of gravity shifts.
You lose that 1-to-1 connection. You have to apply significantly more twisting force at the grip, literally fighting the club with your hands just to pull that heavy bucket back to square at impact.
So think about what this means for you, the listener. If you have been fighting a slice your entire life, and a well-meaning club fitter handed you a softer, lighter, high-torque shaft to help you easily turn the club over and hit a draw.
Oh, man.
They literally handed you a recipe for a high-right miss. They prescribed the disease as the cure.
It completely changes how we view modern shaft profiling. A golfer's feeling of whether a shaft is stiff or soft isn't just about their absolute swing speed on a radar.
What else is it?
It's highly dependent on how they push and pull, how they torque the handle during the transition from backswing to downswing. 2 players can swing at 100 miles per hour, but if one applies torque early and aggressively, a shaft will droop, twist, and feel completely differently than it does for the smooth swinger.
Which means walking into a store, hitting a few balls on a basic radar that says you swing 100 miles an hour, therefore you need a stiff flex, is essentially just guessing.
Absolute guesswork.
And understanding this droop effect leads us to perhaps the biggest revelation in the entire Gears interview, the 14 club problem.
Yeah, this is where it all comes together.
It turns out your standard set of irons, fresh out of the box, is mathematically flawed.
It comes back to the physics of levers. The longer the club, the more centrifugal force is generated, and the more the shaft is going to droop.
Makes sense.
If you put a 4-iron and a pitching wedge on a mechanical robot and swing them at the exact same speed, the 4-iron will droop 3 to 4 degrees more than the wedge, simply because the shaft is longer.
And as we just established, when the shaft droops, it drops the toe, which dynamically flattens the lie angle.
We should probably define those terms clearly.
Yeah, good idea. Static lie angle is just how the club sits flat on the ground when you address the ball in the shop. Dynamic lie angle is how the club is actually oriented when it arrives at impact, bent and drooping at 100 miles per hour.
Perfect. When that dynamic lie angle flattens because of the longer 4-iron shaft drooping, the face points to the right.
And this is the root cause of why so many golfers tend to fade or slice their long irons, but constantly pull their shorter wedges to the left.
Exactly. The wedges don't droop as much, so the toe stays up, aiming the face left.
Have you ever had a range session where you are flushing your 7-iron perfectly, just dead straight, feeling like a tour pro, but then you grab your pitching wedge and you pull it left?
We've all been there.
So you put it away, grab your 4-iron, and slice it right. You probably blamed your swing, didn't you? You thought, I'm losing my rhythm, my mechanics are falling apart.
But it wasn't you. It's because the idea of a perfectly matched iron set is a complete illusion. We look at a shiny new iron set and see identical stickers on all the shafts, assuming they behave the same way.
Right.
But a 4-iron shaft does not have the same flex profile or droop characteristics as a pitching wedge shaft.
The analysts at Gears call this realization the Gears curve, or affectionately, the Nipper curve after Michael Neff.
I love that name.
Imagine plotting a graph where the bottom axis is every club in your bag, from driver down to the lob wedge, and the vertical axis is how much the shaft droops. If iron sets were truly matched, that data would form a flat, straight horizontal line.
But it doesn't. It forms a massive curve. The driver droops wildly, the 4-iron droops significantly, and the wedges barely droop at all.
It's the stark realization that you cannot fit a player by just watching them hit a 7-iron into a net for 20 minutes and then apply those exact same lie angle and stiffness specs to the entire bag.
No, you really can't. Every single one of those 14 clubs is a totally different member of the family, requiring its own specific geometry. Because, as we've seen, lie angle and face angle are absolutely inseparable. You cannot change one without fundamentally changing the other. If the lie angle flattens due to shaft droop, the face point's right. Period.
So you have to measure and fit every single club independently to account for the dynamic droop of that specific length.
You have to.
So how do we actually solve this 14-club problem in the real world? We look at what the touring pros are doing with this exact motion capture data.
They are using high-tech shaft profiling to instantly transform their games. And the best part is, they are doing it without changing a single thing about their golf swings.
The Gears data highlights a perfect example involving PGA Tour veteran Billy Horschel. A few years ago, 2 days before the U.S. Open, he was in an absolute panic.
Oh yeah, he had missed 5 cuts in a row. He felt his swing was great, his coach felt his swing was great, but the results on the course were awful.
He ranked 174th on tour and greens in regulation. He was just clanking it all over the yard.
Yeah, so in desperation, he goes into a Gears facility. He hits his 8-iron, and the optical motion capture instantly shows that the club is coming into the ball almost 3 degrees too upright dynamically.
So the physical hardware of the club face is fighting what his body naturally wants to do.
Yeah.
So what was the fix? Did they rebuild his posture?
Not at all. They literally just did the math. They subtracted his dynamic lie angle from his static lie angle and bent all of his clubs in a vise to exactly 60 degrees.
Wait, really? He didn't change his grip.
Nope.
He didn't change his swing plane. He didn't fire his coach. He changed the hardware to match his natural shaft droop.
And the result? He went on an absolute tear, jumping from 174th in greens in regulation all the way to 7th.
It is unbelievable. Another pro mentioned in the data, Chris Gotterup, had a leaky cut with his long irons that he couldn't fix. They looked at the droop data, bent those long irons 4 degrees upright to keep the toe up through impact, and the problem was instantly solved.
This is why modern club fitting and instruction cannot be separated anymore. You will often hear instructors tell players to lower the handle through impact.
Right. It's a very common piece of advice to improve contact and get the hands ahead of the ball.
But think about the physics. When you lower the handle, you fundamentally change the leverage and the forces applied to the club.
Which changes how the shaft bends, which kills the droop.
Precisely. If your clubs aren't physically adjusted for that new lower handle, a club that fit you perfectly yesterday suddenly won't fit you today. The dynamic lie angle has changed.
And there's another old myth in golf instruction that gets busted by this high-tech perspective. It's the idea that the dog wags the tail.
Oh, this is a big one.
The concept that if you just rotate your big body muscles, your hips and torso, fast enough and clear your left side, the club face will just naturally square itself up through impact without any hand action.
The 3D motion capture data completely debunks that. Look at the profile of Rory McIlroy. The data shows that even with his incredible world-class body rotation, he is still applying massive forearm rotation to square the face.
Wow, even Rory.
Even Rory. The body alone simply cannot overcome the centrifugal forces pulling on that shaft. The hands must apply torque, and the shaft must respond predictably.
So what does this all mean for your next trip to the range or next fitting session?
It means we need to recognize where the problem actually lives. The least invasive change you can make to your golf game is putting a metal club head in a vise and bending it 2 degrees.
That's way easier than a swing overhaul.
Exactly. The most invasive, difficult change you can make is trying to alter your grip or rewrite your natural motor patterns. We have to use the high-tech data to match the instrument to the instruction, not the other way around.
I love that phrasing. Match the instrument to the instruction. We've spent this entire deep dive talking about how your body applies forces to the club, how you bend and twist the shaft, and how the shaft responds. But I want to leave you with one final thought to ponder, based on the fundamental laws of physics.
Okay, let's hear it.
Every action has an equal and opposite reaction. If you are standing over the ball, holding a club that is manufactured poorly, that droops excessively, and twists improperly for your natural mechanics, how much is that club subconsciously forcing your body to move incorrectly before you even reach the top of your backswing?
That's a great question.
Your brain knows the face is going to be open, so it forces you to compensate. Are you swinging the club, or is the club swinging you?
Mm.
If you enjoyed this content, we would really appreciate it if you subscribe to the podcast. Your support helps us continue producing content like this in the future.
It really makes you reconsider that broken diagnostic machine we conceptualize when our swing falls apart. Maybe the patient is perfectly healthy. Maybe it's just the machine that needs calibrating.